Ryōiki Tenkai. The domain and range of a complete quadratic function. We call this complete because all the terms or coefficients are present. We have here f of x is equal to x squared plus 2x minus 15, and we are going to determine the domain and range of this function. Let me rewrite this first in terms of y, because f of x can be written as y. So we have here y is equal to our function x squared plus 2x minus 15. Again, this is considered to be a complete quadratic function because we have here our a coefficient of 1, or we have an x squared term, we have an x term with the b coefficient of 2, and a constant which is minus 15. The domain of this function is a set of all possible values of x that can be substituted here and will yield a real number for our y. If you look closely, if you're going to substitute, let's say 1 squared is 1, 2 times 1 is 2, 1 plus 2 is 3, minus 15, that's negative 12, a real number. Even if you're going to use here 0, you will get negative 15 as a total result, and this is still a real number. Let's say 1/2 as a fraction. The square of 1/2 is 1/4. You have 2 times 1/2 is 1, so 1 plus 1/4 is 5/4. Minus 15, you will have 15 can be written as, or minus 15 can be written as minus 60 over 4. So you will have here negative 55/4, which is still a real number. Even a negative integer can still be substituted here. Let's say negative 2. The square of negative 2 is positive 4. 2 times negative 2 is negative 4. 4 minus 4, 0. Minus 15, which is 15, a real number. Lastly, if you're going to use here, let's say, an irrational number which is square root of 2, the square of square root of 2, canceling the index and the exponent, you will have positive 2, that's an integer. Then plus 2 times square root of 2 minus 15, so you will have 2 square root of 2, then we have 2 minus 15, which is minus 13, still a real number. In this case, with all those values given, and this is the what they call this one, the consistent domain for a quadratic function, it's the set of real numbers. In set builder notation, you will have set of x such that x is an element of the real number. Again, this is always the domain of a quadratic function as illustrated earlier, and this is because you can not have any restrictions here since our function doesn't contain a denominator of variable nor a radical notation with a variable on its radicand. This is simply a quadratic function. Let's proceed with the range. The range now is a set of all possible values of y taken from the possible values of x on our domain. Let us rewrite here. You have y is equal to x squared plus 2x minus 15. Take note that our domain, the set of real numbers, doesn't have any restriction. Will it automatically mean that our range will also be with no restriction? The concern is this. It is true if it's a linear function, but if this, since this is a quadratic function where the possible value of a certain pair of a negative and a positive integer or a negative positive real number will have the same value for the y. In short, there are restrictions here. We can determine that by solving for the vertex. Now, there are a lot of steps to do here, but the step that I'm going to present is the determination of the vertex. And with that, we're also going to illustrate that later on our Cartesian plane to check further whether our analysis is correct or not. The vertex of a quadratic function is indicated by this. Since it's a point on a graph, it is actually called as the point of inflection, or the point where the graph changes its direction. So it contains an x and y value. This is for the x value. For the y value, you have 4 ac minus b squared over 4a. Now, you don't need to worry much on this or memorizing because the value here whatever with the value of that, that is automatically a part of your range, and that's already your hint. Now, you could, of course, try to use the values of a, b, and c here taken from this function. A is the coefficient of x squared, being 1. B is the coefficient of x, which is 2. And c is our constant, which is negative 15. You can substitute that here to get the value of y here, but let me just illustrate in this manner by solving first the value of x, so that if you will ever forget this formula and remember only the x, you can still get the value of your vertex. Now, b is 2, so you have negative of 2 over 2 times a, which is 1. This will give us a result of negative 2 over 2, or in short, our x is negative 1. Now, let's use this and substitute our function. The square of 1 is positive 1. 2 times negative 1 is negative 2. So 1 minus 2 is negative 1 minus 15. You will get a value of y, which is negative 16. Again, you might want to check that using this formula as well. 4 times 1 times negative 15 is negative 60, right? Minus b squared, which is 2 squared, so minus 64. Divided by 4 times 1, so 64, or negative 64, divided by 4 is negative 16. What is this for? That is actually the endpoint of a certain inequality for our range. So it's a set of y such that y is blank, negative 16. So 16 is a starting point, and we're going to determine the direction using the coefficient of a. Our a here is positive, okay, positive 1. Hence, we'll be using this notation and include here equality. This is the range of this given function. This inequality is correct because our a is positive. But if this is negative, we're going to do it the other way around. And the equality will still be inequality because, as you mentioned and as we have shown here by substituting negative 1, y, which is negative 16, is a possible value. Now, to illustrate this further, let's try to use this Cartesian plane. We know that the x-axis is this horizontal axis and the vertical axis is our y. Since our value for our vertex is at negative, okay, our vertex, let me write it here, our vertex is at negative 1 and negative 16. The y value is very large and the grids here do not exceed 10 steps. Let me have it here like per grid is per 2 steps. Take note that if we're going to have 2 steps here, let's say negative 2, the horizontal axis will also have the same range, so or jump, so that our graph would be a little bit accurate. So 1 and negative 16, so negative 1, that's negative 1 here for x, negative 16, negative 2, negative 4, negative 6, negative 8, negative 10, negative 12, negative 14, negative 16. So the vertex is somewhere here. Okay. This is the vertex of the function. To illustrate further the graph, and why do we graph? Again, we need to analyze using a graph so that later on, if the graph is given, you can automatically solve for a domain and a range. We can determine the correct graph of this function, as this is quadratic function. The graph is parabola for at least 5 points. We already have the vertex. We'll be picking the integers below the x value of our vertex and above, which means since it's negative 1, let's have here let's have x is negative 3 and x being negative 2. So you have negative 1 on the right side, x is 0 and x is 1. Substitute all these 4 points or 4 values of x in our function to get its corresponding y. So if this is negative 3, the square of negative 3 is positive 9. 2 times negative 3 is negative 6. Okay? So we have 9 minus 6 is 3, minus 15, negative 12. So 2, 4, 6, 8, 10, 12. And then it's negative 3, so it's somewhere here. So again, 2, 4, 6, 8, 10, 12. This is the other point on the graph. So y is negative 12. If x is negative 2, the square of negative 2 is positive 4. 2 times negative 2 is negative 4. So 4 minus 4, that's 0. We now know that y is negative 15. If this is 0, 0, 0. So y is automatically what retains our constant, negative 15. And if x is 1, the square of 1 is 1. 2 times 1 is 2. 1 plus 2 is 3. Minus 15. So you have here negative 12. So again, negative 2 and negative 15. This is 16 somewhere here. And then 0 and 15. And then 1, which is here. And negative 12. So with these 5 points, this is not a V, but this is somewhere curvy, as you were going to include all the points, including fractions. It will just be something like this. It is called as a parabola. And this graph will continue going up as you include more values of x here and here as well. And that means our domain earlier is correct. Because as mentioned, if you're going to include all points going up and going down to the x-axis, as this graph will go further up and up, we will be including all values of x as there are no restrictions on the graph. So our domain is correct. But as for our range, take note of the vertical movement of y. So as this goes up, all the values here until positive infinity are included. And it will just have the lowest point somewhere here, because this will not be included on our range, because there are no values of x that will give us negative 13 or negative values less than negative 16. It will just end up at negative 16, as this vertex is called again the point of inflection. As the graph changes, as the graph goes to that point in this direction, it will not and will no longer touch the points here at the bottom. In short, the vertex is the lowest point, and the lowest value of y is negative 16. Hence, the domain contains all values of y with negative 16 and all the values above it. That's why we have our range, and this is correct. Set of all y, such as y is greater than or equal to negative 16. So this is how we determine the domain and range of a quadratic function, and this will be the last video for a quadratic function. The domain is still the same as the previous videos, but the range now will depend on your vertex and illustration on your graph. For the next functions, please do not forget to like this video, share this, comment down, and subscribe to our channel. This is for us to expand our domain further.